And hi, welcome to this video. So in this video, I wanted to spotlight a crate I found on Rust because I was pretty interested in OpenCL. Okay, OpenCL. Specifically, I want to use OpenCL for linear algebra purposes, so that if I want to develop my own solver, I can use the GPU to help solve it. Now, of course, OpenCL, if you actually look into the crates, there are some crates available nowadays for OpenCL, but they are very low level. It's not really convenient to use for linear algebra or simulation purposes. However, there's one crate or one set of crates I'd like to spotlight that happens to fit this bill pretty well. Okay, this crate is known as custos or custos. I don't really know if the pronunciation is right, but definitely the crates are useful. Okay, custos is basically what it says here, right? The description says here matrix operation with custos. And what is custos? A minimal OpenCL, WGPU, CUDA, and host CPU array manipulation engine. Now, if you actually go and take a look at the GitHub for custos, you actually see that we are using things like CUDA, OpenCL, BLAS, so on and so forth. BLAS actually talks about the linear algebra libraries. So there are lots of things here. This custos itself is pretty low, well, maybe intermediate-ish level or low level compared to probably what you're used to, or if you're dealing with linear algebra. What you're probably more interested in using is custos math. Okay, custos math it gives you functions to directly deal with matrices. And if you actually go and Google custos math, okay, you Google custos math, you will see that right now there are a few stars on it, about 10 stars, and there are 2 contributors, so do support them. This is quite interesting. This is a Rust library for math in GPU, but it's actually used for deep learning. Okay, if you see here, there's this crate called Gradients by pretty much the same author. It says it's an OpenCL, CUDA, and CPU-based deep learning library. Okay, so enough talk. I wanted to show you what the code actually looks like. Now, I've actually made a binary here, and I've copied some of the code right from the custos math GitHub. And basically, there are 2 things here. Now, over here is sort of me just messily importing things in. So this custos math, you can use for custos math, you can specify CPU and you can also specify using OpenCL. Okay, by default, OpenCL is kind of implemented. However, you will need to, of course, install your own OpenCL. So let me show you, okay, that I've installed OpenCL. What have I installed here? CL info, Lite32 OpenCL NVIDIA, OCL ICD, OpenCL NVIDIA. So this is Arch Linux. I'm actually running the NVIDIA drivers. So the OpenCL that goes along with that is basically OpenCL NVIDIA. And I just basically haphazard installed all these in a haphazard manner, hoping one of them will work. But yeah, that's what I did. I didn't record the prerequisites well, but you just install OpenCL somehow. That's what is needed to get this crate to work, or this library. Okay, so what's going on here? All right, the syntax is pretty simple compared to a lot of other things, a lot of other OpenCL level codes where you actually have to specify memory buffers and everything like that. It's too much things that I don't want to deal with. Okay, this is a mistake. Don't bother with that. Okay, so device equals to CPU. So this is a CPU device. You have two matrices you want to multiply. Here's a 2 by 3 matrix, 2 by 3 matrix, right? 2 by 3 matrix here, and a set of numbers that you want to multiply, right? 1, 2, 3, 4, 5, 6. Okay, and if you want to see what this A is, just put debug, okay, ampersand A. So I'm going to do cargo watch x run. Okay, what is A? A is 1, 2, 3, 4, 5, 6. The first row is 1, 2, 3. The second row is 4, 5, 6. I can of course tell you what B is as well. Okay, B is 6, 5, 4, 3, 2, 1, right? 6, 5, 4, 3, 2, 1 is a 3-row 2-column matrix. So that is the syntax. Okay, C is the multiplication of A and B. So there's this gem thing here. Gem here is matrix multiplication using a global device. That's what the LSP is saying. So it's just matrix multiplication. A dot gem and B. So C is what is gonna come out. Okay, so that's the basic example in the README. Now the first time you actually compile it, there will be some problems, but basically follow the compiler advice or stick around to the end of the video. Or maybe, yeah, I'll deal with it in another video. All right. But yeah, just want to show you the features. Okay, so this function is called using OpenCL. So we have talked about using CPU, which I don't think is that interesting if you are already like setting your sights on GPU using graphics cards to compute your math. Okay, and that's what I found was quite interesting to at least try out in Rust. So that here you go. Okay, of course CPU is the bread and butter. CPU computing is the bread and butter, but yeah, GPU is a slightly more exotic. So how do you use it? Okay, we use a similar syntax here. OpenCL new, and then the number is 0. I don't know what this is. Oh, it's called the device index. This is the device index. Okay, so device index is 0, and then you just unwrap it. It's a result. Okay, the syntax for creating matrices is the same. Over here, you have to specify that the device is a CPU. You have to specify the dimensions here, and then you have to specify an array of numbers right here. Okay, same thing here. Specify the device. This is an OpenCL device. Okay, it's an OpenCL capable device. Okay, 2 by 2 matrix. Okay, so this is a relatively simple calculation. I think you can use a shader for it as well. Shader is a calculation unit of calculation, I guess. I'm not really getting my terminology right, but it's used for graphics. Okay, so but I'm pretty sure, well, we can test out next time if we can deal with larger matrices than 4 by 4s. Maybe a 5 by 5 matrix will be quite an interesting thing to try out. But here's what we have in the example so far. This is a very simple example. So 0.25, 0.5, 0.751, and then 1, 2, 3, 4. Okay, we have a simple multiplication here. C equals to A times B. Okay, and you won't be able to use A or B after that, I believe. If we debug C, you'll get 0.25, 1.0, 2.25, and 4. That's what the last part here is. That is that. Then there's the assert equal here to the answer, and there you go. That's, well, you use OpenCL to perform calculations. So as you can see, the syntax is not as involved as learning OpenCL using C++ or C for that matter, where you have to allocate memory manually. Of course, there is a lot of value in learning that, but if you don't want to deal with that, this is one possible option that's under development. So just want to say, hey, good job. I don't know how to pronounce this. Elf thousand. Oh, yeah, 11,000. 12,000 maybe. I don't. Maybe that's the idea. Um, yeah. So good job, whoever these two people making custos and custos math. Good job, good job. I think it's a interesting crate to explore if you are interested in GPU programming. Getting it to work is still kind of tricky. Requires some debugs, and I'm not going to. Oh, I could do it. Oh well, why not I just do it for you? Yeah. So what I'll do is, yeah, here is. Hold on. Okay. So anyway, here I have already a project that's capable. So I'll need to show you, well, how to so-called start one from scratch. I call this the OpenCL playground. Okay. Let's go to YouTube. This is where I find all my YouTube projects. Okay, so I'm going to do the same thing again. Cargo new OpenCL playground. Okay, so I made a OpenCL playground package. So here's a cargo.toml. I can use tmux here just to give myself a little more tabs. And I'm going to use neovim as usual. Cargo.toml is here. There are no dependencies. So what do I want to do? I'll make another tab, and I'll do cargo add custos. Yeah. Okay, you will see that here there are only two features out of everything. One's a CPU, one is OpenCL. If you don't want CUDA or anything else, this is really all you need. So we'll just leave it be. Okay, press :E to reload, and you will get this. Okay, you will see custos math is by default given 0.63. Okay, and then here's the main just saying hello world. Now, of course, you don't just want to do hello world. You want to do some calculations here. So here's the example in the dot. Just copy this and paste it into your main. Paste it here, save it, and you will find that there are some errors here the first time you actually compile. So if you actually do cargo build, you will have a problem. You see here, the type annotations are expected. Let me zoom out a little bit more. Type annotations are expected. And then you're kind of lost a little bit. So let me just run you through what to do, or rather what I did. Okay, so what I did was a very simplistic way. I'll just turn on cargo watch -x run, so that every time I save, I will get what do you call that? I will get changes that are reflected, so it's easier to debug. So what I'm going to do, I'm just going to copy and paste all of this here. I'm going to copy and paste all of this here. Okay, if you have a LSP, that's even better, but I'm doing it in case you don't have an LSP. Okay, so what does it say now? It says OS is not found. Okay, what I did was just to leave it blank. Okay, like an underscore. And then what does it say here? We cannot infer the type of parameter OS declared. Okay, so a.gem : is a bracket and an OS here. What does that mean? Okay, the best way to find out is perhaps you can actually go to the definition of gem. I'm going to go to the LSP there. All right. But if you don't have an LSP, then you gotta go to the GitHub or something like that, and you check out what gem is. I'm going to give you this, right? You'll see here that the generic parameters here are the RS and OS. RS here is a shape. OS is also a shape. Now, my conjecture is that since RS is a blank or bracket, it's a void shape. OS can also be a void shape. So I'm just gonna try this out. Void shape and void shape. And then cargo run. Okay, so that's what I did, and it happens to compile and work. Strangely enough, this only needs to be done once. So let's see equals a dot gem and b. Okay, if I do this a second time, okay, this time around I still need it, but if I do this a second time, oh, funny, this is still needed. Okay. Okay, so I guess it's still needed. But funny thing is, well, let me try the GPU portion, and I might as well show you the code, and then you'll see why the code is written like that and it still works. Okay, so let's go to examples. Now I'll show you the simple.rs. Okay, I'll copy this opencl using opencl, and that's how I construct this. And I'm not going to use the result because it's more cumbersome to import more things. I'm going to delete the OK at the back. OpenCL can be imported. Okay, so I'll just put over here custos OpenCL. How do I know that? You go to the top here, you'll see custos OpenCL right here. Okay, so I just put custos OpenCL right here. Custos OpenCL. Okay, and I'll take away the question mark operator, and I'll just put unwrap. Okay, and then I'll put using OpenCL. Okay, somehow things work. Now, let me try this, yeah? Let C equals to A gem and B. And let me go and copy and paste all of this in. All right. This is really weird. I can't repeat the error for some reason. Okay. Well, this is most peculiar. As you can see previously, if you saw previously in the earlier parts of the video, this was not a problem. But in any case, yeah, I don't know why the bug was not repeatable. Maybe it's a race condition or something else. I have no clue. Okay, but this actually just seems to work as is. All right, so if you run into this problem and if you run into this problem of having the type annotation thingy, you can actually just read the compiler logs and guess your way through. This is what I did. I don't know if it's always usable, but it made the examples work this time around. Okay, so I think that's it for today. Yeah, I just wanted to spotlight Discrete as something quite promising if you want to use OpenCL in a rather easy fashion, or rather high level-ish library, so that you can do algebra, matrix multiplication, so on and so forth. Pretty good. Okay, so I think that's all for now. I'm gonna call it a day, and I will see you guys next time.